going to throw out to you some I'll just answer here. So variables, we talked about x, y, dx, and dy, where we say x was the time since the flag started lowering in seconds. And then we said dx was a change in time, any change in time since the flag started lowering, okay? And then y was the height of the flag above the ground in meters, and then dy was a change in the height in meters, okay? And how are those variable and not just a symbol for an unknown fixed value? Anyone want to answer that question? So x, right? You think of x, at one point in time in the history of the world, this flag started coming down, and that's when x started at 0, right? And the flag was coming down. Now x is increasing, right? X is increasing. So we don't want to think of x in this situation as an equation, something we're solving for to get an answer for x. X took on every time starting at 0 since that flag was lowered. Okay. Rate of change. What was the rate of change of height with respect to time? Negative 0.75 units, meters per second. Negative because we define height as positive up, and as time increases, that height is coming down. So our rate of change is negative because we have a decreasing value of y, or the height of the flag. All right, the fullest meaning of this rate of change. So first of all, what's the narrow typical meaning? If the rate of change is negative 0.75 meters per second, what's the narrow meaning? What's the narrow meaning? Do you remember from Friday? Yes, sir?
Each second it goes down 0.75 meters.
Right. Each second, the flag goes down negative 0.75 meters. But on Friday, we said, you know a whole lot more than that, right? You know how far it goes down in 1/10 of a second. You know how far it goes down in 1/2 a second. You know how far it goes down in 3 seconds. So given any change in time, that rate of change tells you how far it goes down. So how far does it go down in any change of time? Somebody knew. How far does the flag go down in any change of time? Yes, sir.
Negative 0.75 times that change in time.
That's right. So given any change in time, and we called that on Friday, we called that dx. The change in height is negative, what he said, negative 0.75 times that change in time, right? If it's 10 seconds, we know how far it goes down at that constant rate. We know it goes down 7.5 meters. So you take negative 0.75 times the change in time, 10 seconds. That gives you the change in height. Okay, so this equation frames the meaning of that value. See that? This equation frames the meaning of that value. Given any change in time or any dx, we always know what dy is. Okay, so that's the best definition of that. Broadest and fullest. Okay, so how do we create this function then? Where did this function come from? What was that? That was the net accumulation function, negative 0.75 times x minus 0.6. Well, it came from this, right? It came from that because we wanted to get every change in height given a change in time starting from 0.6 seconds, right? Given a change in time starting from 0.6 seconds, that's our x minus 0.6. We wanted to know what was the corresponding change in height, and that was the dependent variable. So dy is the dependent variable of this function. And since we were saying we want to know the change in height 6.6, we took final time minus initial time to get our change in time, dx. Okay, so the meaning of the function is, the independent variable is, what, x, time since the flag started heading down. And the dependent variable is change in the height. Which change in height? Since 0.6 seconds after the flag started lowering, right? So it's the change in the height starting since it was 0.6 seconds after we started lowering the flag. Okay, that's our dependent variable. Okay, meanings of the points. So here are those two functions graphed, the rate of change function, and then this net accumulation function. So someone new, volunteer, what is the meaning of this point right here? So understanding individual points on the graph of a function is really almost understanding the function, right? Yes, sir.
It's the rate of change in the height at time 1 second.
Okay. So is that point solely, so 99% correct. Is that point, does it mean the rate of change? Does it mean the rate of change?
It's the rate of change at time.
Right, so it's both values together, right? So yeah, so the point doesn't mean the rate of change, but it means that at 1 second, the rate of change is -1, negative 0.75. So yeah, you had everything perfect except that the point is both values together. The point represents both values taken together and not just the rate of change. Okay? So then what would this one be? At 2.3 seconds, the rate of change is still negative 0.75 meters per second. And so then what is that red line? What is that red line? Hint, we just explained two of them. The line is not the rate of change. The line is...
Change of the flag's height.
Okay, so I'm asking this question after we talked about two individual points. So, right. It consists of all of the points that tell us the rate of change at any time, right? All of the points. This just takes too long this way, right? This just takes too long to draw it this way, you see? But you have to think of it that way. You have to think of it that way. When you see a line or a curve, you have to think of it as a mess of points. A mess of points. Each point having the information that we talked about for those two examples. It's just that we just swipe our pen across the page to represent it. But what are we doing? We're representing a whole lot of points. A whole lot of points. Okay? Think of it. So that has to be your image when you look at a graph. And then each point is what we said, what we described. Two values of the variables taken together, right? Okay, so let's just do this one right here. So who can tell me the meaning of that second point on this graph? Somebody new. The meaning of that point. Yes, sir.
The net change in height at x equals 1.6 seconds.
So at 1.6 seconds, you said? You said the net change in height was? Is that what you estimated? Negative 0.7. So at 1.6, the net change in height was negative 0.7. And which net change in height was it? Which net change in height was it? So there's one more detail we want to include. So yes, at 1.6 seconds, but this number, this negative 0.7, is the change in height since 0.6 seconds, right? Since 0.6. Okay, so since 0.6 seconds, the change in height is negative 0.7 meters. At 1.6 seconds, right? At 1.6 seconds, since the flag was started to be lowered. So that this is x, right? This is time since the flag started being lowered. But then this number is the change in height since 0.6 seconds after the flag was being lowered. Does that make sense? That's why at 0.6 seconds, what's our net change? Yeah, 0, right? At 0.6 seconds, our net change is 0 because that's kind of our reference point. Okay, any questions on this worksheet? Okay, so we're moving on to principle 3. Okay, again, what are these? All these principles are about this. We're reviewing the mathematics of, you know how fast the quantity is changing at every moment? You want to know how much of it you have at every moment. Okay? Principle 3 is changing rate of change. Changing rate of change. The example that we just went over was a constant rate of change. So let's think about a soldier lowering the flag. He's doing it by hand. How likely do you think it is he's going to be able to maintain a constant rate of change pulling that flag down? Okay? So I propose maybe it's something more like this. I want you to take 30 seconds to a minute to talk about why it might be something more like that. Okay, now compare to mine. Now compare it to mine. See how you did. So yeah, if that rate of change is going to head towards 0 at about, what, 1.2 seconds and around 2 seconds, then you're not going to see, for that small interval of time, you're not going to see much change, right? You're not going to see much change. So that's why you have these little levels out, or these constants in terms of the total amount of change at around 1.2 and around 2. Okay, so what does this have to do with this thing that we're reviewing? You know how fast the quantity is changing at every moment? You know how much of it you have at every moment. What does these functions, these graphs, have to do with that? So, you know how fast the quantity is changing at every moment. First graph. Right. This is the rate of change, right? This is exactly what a rate of change function tells us. Given any moment since we started lowering the flag, there's a point that tells us what the rate of change is at that moment, right? Okay, and what about, you want to know how much of it you have at every moment? Okay, so maybe we think of how much of it you have at every moment as just the height of the flag at that time, right? But would you agree that the height of the flag is very closely related to how much change we've had, right? So it'd be one easy step to get from amount of change to height. So we can, so in terms of the rate of change, our notation for that would be then, this is exact rate of change function, r sub h. We're interested in the height function, right? So the rate for the height, okay? The exact rate of change, all right? And then how much of it you have? Well, the amount of change is virtually almost the same as that. There's one easy step from amount of change to actual height, okay? One easy step, okay? So we call that a sub h, right? So the accumulation of changes in height, right? And we say that's just one step away from the actual height function, an easy step, okay? So now, here's the big question. How do we write this net accumulation function when the rate of change is changing? Okay, it just got a lot harder, right? Because when we had a constant rate of change, piece of cake, we knew we could calculate these changes really easily, right? dy equals m dx, because that m is constant. So we could always get the change just by multiplying m times whatever change in time we were talking about. But now the rate is changing, and it's changing moment by moment. So this becomes more complicated. This becomes harder, okay? But this is the very question that we've finally gotten to the actual question of, you know how fast the quantity is changing, you want to know how much of it you have, okay? So how do we do that? How do we do that? So let's take a look at that exact rate function again here. I've got it on graphing calculator. We've got this changing rate, but really to calculate changes, and then eventually height, we really need constant rate of change, right? Constant rate of change is our ticket because the math is easy. with constant rate of change, we can calculate changes. So we want to use that here. And what we want to do is we want to create a new function that's simulating that one, trying to be like that one, pretending to be like that one, but made up of all constant rates. And then since we have constant rates, then we can use the math that we've just been working on, right? So what I want to do is we want to start at 0.6, and we want to use intervals. So we're going to use delta x to mean not a variable now, but intervals of time that always stay the same, 0.35 seconds. So delta x, this is not a variable, but what we call a parameter. So in our situation, it's going to hold that value of 0.35 seconds, and I've marked that off starting from 0.6. So in each of these intervals of 0.35 seconds, we want to pick a constant rate that's trying as much as it can to be like this rate function. And then with those constant rates, then we can make headway at calculating changes, right? Okay, so in this first 0.35 seconds, what should we pick to simulate the rate of change? So that's in this first interval here. So interval number 1. What should we pick? And that's an easy one. Yeah, the negative 0.75. So I'm going to do this in red. So we're going to do negative 0.75. Okay, now we look at the next interval. And we say, oh, let's see. So it goes up to 0 and back down. So maybe, maybe the best guess is half of negative 0.75. Something in the middle. So I'm going to call that negative 0.4. And so let's write this down. So now we're going to use just r without a subscript to mean approximate rate of change. So this is negative 0.75. This one's negative 0.4. What about the next one? Yeah, and so this is just about getting something close. There's, if you were to do this and I were to do this separately, we might have different numbers. We probably would. Okay, now this one, we've got all the rates between negative 0.75 and 0, but then we've got this string of negative 0.75s kind of pulling it down, right? Pulling it down. So for that one, I'm going to say negative 0.5. Oh, sorry, I didn't draw this one. So we're going to draw. Okay, right? I'm going to draw that. And I'm going to draw this. So this one's going to be negative 0.5. And then here we see kind of the same idea, but we got more of the interval at negative 0.75. So more weight towards pulling it down. So I'll say negative 0.6. So do you get the spirit of what I'm trying to do? I'm trying to pick one rate that might kind of, be the same overall effect as this changing rate in that interval. So the next one is kind of the mirror reflection of that last one, so we'll keep it at negative 0.6. And then the next one, if you look, is kind of the mirror reflection of this one back here. So we'll go back to negative 0.5. And then the last one, back to negative 0.75. So what have I done? I've drawn a new function that's trying to be like the changing rate function. I've drawn a new function that's trying to be like the changing rate function as best we can, but then using constant rates over intervals of 0.35 seconds. And we're going to call that function r. Okay? So now we can generate a net accumulation function, but now this is going to be approximate, right? So this is what we call the approximate rate of change function. Or it's there will be lots of ways to do this, but this would be a approximate rate of change function. And then from that now, we're going to work on that to get a net accumulation, like we were doing before. Okay, but so now we've got it split up. Okay, now we've got it split up, so we have to do it like a little piece at a time. Do a little piece at a time. So we can ask ourselves, starting from 0.6, how much change do we see by the end of that first interval, say at 0.95 seconds? How would you calculate the amount of change, or the net change, since 0.6 seconds at the rate negative 0.75?
X value times the rate of change you've estimated. So it would be 0.35 times negative 0.75 in this case.
Right, if the rate of change is negative 0.75, we know that given any change in time, the change in height of the flag would be that rate times the change in time, right? That's what we talked about for our meaning for a rate of change. Okay? And then we come into interval number 2 here, and what do we say? Negative 0.4. So then how would we find, I want to know the net accumulation of height according to the red function at 1.3 seconds. So I want you to explain to the person next to you, how would you find the net accumulation of height since 0.6 seconds at 1.3 seconds? Explain to the person next to you. Somebody new.
Sum everything up to that point for each interval.
Okay, so she said sum everything up to that point according to that interval. So be specific about what do you want to sum up? Yeah.
You take the first interval, the rate of change of that interval times the amount of time change.
Okay.
The dx of that interval.
Right.
And then so you get that value, and then you get the one to the next interval, and then you just kind of sum everything up to the point that you're trying to find.
Okay. So she said that you would find the amount of change for this first interval by taking the negative 0.75 times 0.35. And then you would go to the next interval and find the amount of change from that interval, which would be, this would be negative 0.4 times 0.35. But then you'd have to sum these together to get the net accumulation of change. And then you'd continue to always, as you calculated the change in each new interval, you'd continue to add all the change from the previous intervals. Agree with that? Okay, so we're not going to do all the math of that, but I do have that. There we go. Okay, so here's what happens when you do that. Here's the rate of changes that the rates of change that we estimated to form our pretend rate function, and then here's the amount of change in each individual interval, and then what is this, an accumulation function? So we're accumulating amounts of change then in each interval. Okay, so it would be good to, if you're reviewing the video, do the calculations. Don't look at this, but do a few calculations and see if you can reproduce this. That would be a really good exercise, so you really make sure you understand what this is doing. Okay, so we get a net accumulation of height. And so this is a set of ordered pairs now that represents the approximate accumulation function. So at 0.6, we've accumulated 0. At 0.95, there's our total accumulation, etc. So these ordered pairs, first and last column, are all points on our net accumulation based on our approximate rate function. So therefore, that's an approximate net accumulation function. Okay, so in your homework, you're going to be, it's a 4-page worksheet. It's not from the online textbook. I'll post it on Blackboard in the next 15 or 20 minutes. Okay? And so this is going to review, all this stuff, maybe take some things a step further, but you can do it. And if you need help, office hours. Office hours. All right, good. Glad to have you.
Awesome.
Yeah. Sure.
Are they supposed to be lined up like the 0.0?
No, because these are values of x, right? These are moments of time. Our rate extends across an interval, right? So the rate goes from 0.6 to 0.95. Okay, and then we get an amount of change for that interval, right? We get an amount of change for that interval. Then what we want to know then is how much was our net accumulation at the end of that interval. So those match up with this. Okay? So what happens is, we start at 0.6, 0.95, we're at this rate, we see that much change. Now at the end of the second interval, we have this much change.
Okay, that makes a lot more sense.
And then in the next interval, we have this rate, we see this much change. And so then at the end of that interval, our total accumulation of change is that. Oh yeah, so that's really good question. So don't, because that would be great if I would explain that. Like I just was explaining it. So ask in class. Make sure, if you're not sure in class, don't hesitate to
To
ask.
explain again.
The same thing?
Yeah.
Same thing?
Yeah, I'm very lost.
Okay, so these are the endpoints, end time intervals of our intervals, right?
Yeah.
These rates extend across an interval, right? We had a rate of change that started at 0.6 and ended at 0.95. So that rate goes across through that interval. We went in the middle. And so this rate starts at this time and ends at this time. So then we get an amount of change at that rate across that interval.
And that's 0.35 times negative
0.35 times negative 0.75.
So
And
every
by
time.
the end of the interval now, when we get to 0.95 seconds, we've accumulated this much total change.
Okay.
Now we go to the next interval from this time to this time.
So from here to here, it's like it's still 0.35 times that.
Right,
to get
gives you that.
But that was accumulated from this. And
Now we get the total accumulation of the first two intervals.
Okay. Okay. That
Yeah.
makes sense.